Dropping a spoonful of sugar into water creates a homogeneous mixture, tracked by a simple equation. Solute plus solvent equals solution. In binary solutions, quantity defines roles. The smaller amount, sugar, is the solute. The larger amount dissolving it is the solvent. This table shows that solutions exist across all physical states. A solvent can be a gas, a liquid, or a solid. Air is a gaseous solution of oxygen and nitrogen, while an amalgam of mercury and sodium forms a solid solution. For precise chemical reactions, we need a quantitative measurement of the solute hiding inside the solvent. We call this concentration. To express concentration, we use mass percentage for solids, volume percentage for liquids, and parts per million for trace pollutants. Mole fraction relates target moles to total moles. Crucially, liquids expand when heated, making volume-based metrics change with temperature, while mass-based metrics remain constant. Categorizing these formulas by whether they use volume or mass allows you to answer temperature-related questions logically, without relying on rote memorization. Two primary concentration metrics look similar but operate differently. First is molarity, represented by a capital M. It measures the moles of solute per liter of solution. The denominator is the volume of the entire solution. For a solution of 5 grams of sodium hydroxide in 450 milliliters, we convert the mass to 0.125 moles and the volume to 0.45 liters. Dividing moles by liters gives a molarity of 0.278 m. On the right is molality, represented by a lowercase m. Instead of the volume of the whole mixture, molality divides the moles of solute by the mass of only the solvent, measured in kilograms. To find the molality of 2.5 grams of ethanoic acid in 75 grams of benzene, we find our moles of solute, 0.0417, and convert the solvent mass to 0.075 kilograms. This result is a molality of 0.556 m. Notice the exact difference in those denominators. Success with these problems depends on whether you are using the volume of the solution or the mass of the solvent. Test your understanding by solving this. Calculate the molality of 2.5 grams of a solute with a molar mass of 50 dissolved in 100 grams of solution. If you used 0.1 kilograms as your denominator, your calculation included the mass of the solute. Molality requires only the mass of the solvent. We must subtract the 2.5 grams of solute from the 100 grams of solution, leaving 97.5 grams of solvent. After converting 97.5 grams into 0.0975 kilograms, we divide our 0.05 moles of solute by this accurate solvent mass. The final molality is 0.513 m. Recognizing the phrasing solution mass versus solvent mass in a word problem ensures you use the correct value for your denominator. Consolidating these formulas reveals the core pattern behind Chapter 2. Comparing them side by side highlights the critical role of the denominator. Molarity uses liters of solution, while molality uses kilograms of solvent. When a problem provides mass percentage and density instead of direct mole values, this formula calculates molarity in a single step: mass percentage times density times 10 divided by the molecular weight. The golden rule of these calculations remains temperature dependency. Metrics that rely on volume change as the lab gets warmer or colder. Metrics based on mass remain constant. Use this table to review the specific units required for each calculation. Now that the math of concentration is clear, we can move to the mechanics of gas solubility and Henry's law.